Okay, so we were in the middle of something last time, and I want to pick up at that point, or maybe go back just a tad, and then finish chapter 3, and then answer your question about the what happens for rotations, in fact also boosts, rather than just translations in space and time. Okay, well, we saw, let's see, we saw that the inhomogeneous equations of electrodynamics look like this. So the divergence of F is the current, and if you write down what that is, and you go to the Lorentz gauge, then you get the equation box A d, say, equals JD. And we were talking about that last time, and Schwartz likes to use the notation 1 over box. And this 1 over box is the propagator, and you might say, well, what is 1 over box? The propagator for the A field then is 1 over box, and the question is, what's 1 over box? Well, in order to see what 1 over box is, we need to think a little bit about Fourier transforms, and Fourier transforms make it easy to think about things like this. And in particular, last time I think we were saying that delta cubed of x, well, this is an integral d cubed k 2 pi cubed e to the I k dot x. And so then Laplacian on delta cubed of x is what? Well, this is an integral d cubed k, and then you get minus k squared here because of the I. And then again you have 2 pi cubed. I'm trying to avoid the wet part of the board. And in fact, it's easy to see that you can iterate that and say you have delta n on delta cubed x is an integral d cubed k over 2 pi cubed. It's then minus k squared to the n e to the I k dot x. Okay, now needless to say, these integrals are divergent. Okay. And so something like this makes sense only when it's surrounded by other functions that, are smooth or that vanish rapidly at large values of k, or are smooth at small values of x, and so forth. So, so you need to be a little bit cautious there. A four-dimensional delta function, one is for space-time, is an integral d4th k 2 pi to the 4th e to the I k dot x, and that's now the Lorentz product, and so you see, well, we've got d4th k is Lorentz invariant, k dot x is Lorentz invariant, so the delta function is Lorentz invariant. You can then consider box on d4th x. Well, this is an integral d4th k 2 pi to the 4th, and that would be time derivative squared minus the Laplacian on e to the I kx, and so this brings down a minus k0 squared, and then we have plus k vector squared. So altogether, this is an integral d4 of x over 2 pi to the 4th minus k squared e to the I kx. And consequently, once again, you can say, well, box n delta 4th of x is an integral d4th k 2 pi to the 4th minus Lorentz k squared to the n to the I kx. And what makes a little more sense here is that if we have a smooth function f, then box, well, all right, box to the n if you want, on f of x is an integral d4th k 2 pi to the 4th f tilde of k e to the I kx. This is the Fourier transform of f, and then we have box to the n here, and box to the n brings down minus k squared to the n. So again, this makes sense only if f is smooth at the origin, which is to say that this thing goes down rapidly at large k. Any question? All right. So these electrodynamics equations now that we have a dry board for a static charge, there's no movement, and so the spatial current is 0, and what we've got is A0 is E over a box x. So this in a certain sense, this is x, y, y, because as we see this, as we'll see in a moment, this is an operator. You can view it as a matrix, and we'll see it's an integral, very much like these integrals. So this is the solution. Apart from solutions, box a mu equal to 0. In other words, you can have also plane waves that don't have anything to do with the static charge. So this is KKOB, which I recommend you turn off. All right, so we're talking here about the Coulomb potential then, and in Schwarz's metric, you can let this 0 here fall under the weight of gravity. You can just fall down to here and there's no change because of Schwarz's metric. And in fact, there are time derivatives here, but there's no time here. So what we wind up with then is A0 is minus E over Laplacian, and that's because box is d by dt squared minus Laplacian delta cubed of x. All right, and what we really mean by that is an integral d cubed k 2 pi cubed. And now what's 1 over Laplacian here? Well, let's just say let's just posit that this is the answer. E over k squared, e to the I, k dot x. And now why is this true? Well, if you multiply this thing by Laplacian, this pulls down a minus k squared. That then gives you a delta function, and so this is, so in other words, what you get is minus Laplacian on A0 is minus E integral dqk over 2 pi cubed. The k squareds cancel, the minus sign came out, e to the I kx, and this is just minus E delta cube of x. So that's then a solution to the differential equation. So now what is this? Well, I suppose it's worthwhile doing the integral explicitly, but if everybody wants to skip the integral, I'll skip the integral. So give me some advice. Should I do the integral? All right, I see one no vote, three no votes, but maybe there's a yes vote somewhere.
Can you describe what the integral is again?
What?
Can you describe what the integral is?
Ah, there's a yes vote. All right. What is this integral?
Oh, that.
A0 of x, it's e over 2 pi cubed, well, what the hell? Integral 0 to infinity, k squared dk, integral minus 1 to 1, d cosine theta, integral d phi 0 to 2 pi, e to the I kr cosine theta over k squared. So that's the integral. And now that I think about it, it's a little bit, it's not a totally trivial integral. The phi integral is trivial and just gives us a 2 pi. And then we're left with A0 of x is e over just 2 pi squared, integral 0 to infinity, k squared dk, minus 1 to 1, d cos theta, e to the I kr cosine theta. Well, that's a pretty easy integral to do. And what we get is e over 2 pi squared, integral 0 to infinity dk, e to the I kr minus e to the minus I kr over I kr. And we can, so this is 4 pi squared. We can change this to 8 pi squared and pull out the IR if we integrate from minus infinity plus infinity dk. What happens is when you go to negative k, this flips sign, but these guys flip sign also. So it's e to the I kr minus e to the minus I kr over k. So that's the integral, and it's worth doing because, well, it's an example of conjugate integrals. Now, near k equals 0, the one term cancels, and so this is like 2I kr. Then the k cancels. And so this thing is basically, the k dependence is basically, I mean, there's no k dependence. It's just simply a constant near k equals 0. And so what we can do then, if we imagine if it's a constant and we imagine just a very tiny bit of the dk integral there, of length epsilon, say, how that behaves really doesn't matter because it's just of length epsilon. And so what we do is we change this to put in an I delta, and that means that this integral here has just sort of a bit of a hole there. And so now what we can do is add contours, and I like to call these ghost contours. And the first one, what we do is we add a ghost contour like this, and and we just get 0 for this term. Why do we add this ghost contour? Because when k is way up in the positive imaginary part of the plane, say I infinity, this is minus infinity times r. So this contour doesn't contribute, and the first term vanishes. On the other hand, the second term, though, we have to add a ghost contour down here, and so that extra contour is 0, but now we have a loop integral around the pole, and so that gives us E over 8 pi squared, 1 over IR, and then 2 pi I, and I say 2 pi I because there's a minus sign here, and because we're going clockwise rather than counterclockwise. So it's 2 pi I E to this thing evaluated at k equal to I delta, and so that's just delta R, and then in the limit delta goes to 0, that's just 1. So altogether the answer here is E over 4 pi R, and that's of course the Coulomb potential. So that's, I guess, comforting. Any questions? All right. And in general, what you can do is you can say that A mu is 1 over box J mu, and I guess if you're taking the E and M prelims, you can always just write that down and you get a point or two, I would hope. But they probably want more. I've been trying to get rid of the prelims. I've voted every time. 31, 25 to 5. Okay, so suppose we're looking at an action density that's minus a quarter F mu nu minus phi star box phi. I'm not terribly fond of that notation because he's done an integration by parts here. I mean, it's okay, but I would rather write that as and then minus IE, let us say A mu phi star d mu phi minus phi d mu phi star. Okay, so this is a scalar field interacting, a charged scalar field, a complex scalar field, charged interacting with the electromagnetic field. And once again, if we go to the Lorentz gauge, d mu A mu equal to 0, what we have is box A mu is IE times all of this, which is phi star d mu phi minus phi d mu phi star. And we can say, well, this is, we can just call that J mu. And then we would say, well, A mu is 1 over box J mu. And we could go through the whole thing. So, any questions? All right. What does gravity look like? Well, for gravity, the action is something like this: 1 over Newton's constant. And now I'm using not simply natural units, but units where 2 and pi are equal to 1, and minus 1 as well. So this is R square root minus G d fourth x. So that's basically what gravity by itself. G is the determinant of the space-time metric, and R is the scalar invariant that's quadratic derivatives of this, and And so what people do who want to do this thing perturbatively is they say, well, let's let G mu nu equal to eta mu nu plus square root of G H mu nu. And then if you look at the equations and you say, well, G is very small because gravity is weak unless you're near a planet. Consequently, you can do perturbation theory in big G. And it's rather funny, actually, perturbation theory in gravity. I mean, if ever there was a coupling constant that was small enough for perturbation theory to be reliable, well, it sure as hell is gravity. On the other hand, gravity is non-renormalizable, so because of the infinities that occur in the ordinary theory of gravity, you can't actually do perturbation theory. You have all these crazy infinities that you have trouble with. Anyway, so it's a puzzling sort of paradox there. In any event, let's nonetheless thrash ahead, just pedagogical reasons, and let's ignore these pesky indices here and think about something that we can think of as scalar gravity. All right. And if we look at scalar gravity, then the reaction density looks something like this. Minus a half. Actually, did I say a minus sign here? It's a minus sign in the metric I normally use, but it's a plus sign in the metric that Schwartz uses. And that's why it's minus with the box, because when you integrate by parts, you get a minus. So, in other words, if you had something like a half d mu h, d mu h, and then plus, let us say, a third lambda, where lambda is something like square root of g, h cubed, plus some constant j. J is not a constant. J is a current. It would be a source term. It would be energy momentum of matter fields that couple into this scalar gravity. And so then our field equation would be something like this. It would be 1 over big G square root of g h cubed, which is something like square root of g h cubed. This is the interaction, I should say. And this we're setting equal to 1/3 lambda h cubed. So lambda is square root of big G. And now our equation is minus box h plus lambda h squared plus j equals 0. And don't worry too much about details here, because we're just sort of illustrating things rather than actually trying to precisely calculate anything. So the field equation is box h is j plus lambda h squared. So we'd say this is the matter or the energy that causes the gravitational field, and this is the interaction of the gravitational field with itself. And that's pretty.
How did you go down 1 power in h on everything?
Oh, good question. Over here, what we would do is we would say, well, the equation is, partial L d mu partial L partial d mu h equals partial L partial h. Okay, that's Lagrange's equation. This gives you the box, or minus box, whatever, and you differentiate with respect to h, you come down to h squared and j. Good question. I don't know if you were serious or just hungry, but Okay, so this is the equation. The lowest order, what we would say, is a box H0 is J. So H0 is 1 over box J. And then we would say H is H0 plus H1, so we'd have here box of H0 plus H1 is J plus lambda H0 plus H1 squared. Okay. And this leaves us with, since box H0 is J, we know how to solve this, basically the way we solve things in the front there. We have then box H1 is then equal to lambda H0 squared if we ignore H1, which is because H1 is small. And so then we say, well, H1 is lambda 1 over box times H0 squared. And, okay, so what is that? So then that means that this is lambda 1 over box, but now what's H0 squared? Well, H0 is 1 over box J, so this is 1 over box J times 1 over box J. And so our equation then for H is 1 over box J plus lambda 1 over box J 1 over box plus higher order terms. Now we have this, the propagator here is minus 1 over box. This is called the Green's function of the propagator, and the idea is that box, this is pi, Greek letter pi. Box x on pi of x and y should be minus delta 4 of x minus y. Okay, so now you recognize that this thing is a Green's function because hitting it with a quadratic differential operator gives you a delta function. That's what we mean by a Green's function. And of course, box is what we know what box is. All right, so what is this pi of x and y? Well, it's integral d fourth k, 2 pi to the fourth, e to the I k x minus y over k squared, because now if we hit this with box, what we bring down is minus k squared, and that gives us, so in other words, box on pi of x and y gives us an integral d fourth k 2 pi to the fourth minus k squared over k squared, so that cancels apart from a minus 1, e to the I k x minus y, and that's just minus delta 4 of x minus y. Okay, so that's why that's the solution. And now, no doubt you say, well, shouldn't we say something about how we regularize k, 1 over k squared, k equal to 0, and yes, we should put in an I epsilon or something, but we're not going to bother with that at this stage now. Okay. Notice that this is symmetric. This is the same thing as pi of y and x, because if you flip this sign, that's the same thing as just integrating, instead of integrating over the first quadrant first, you integrate over the 16th quadrant first. And, so that's that. All right, so what is this solution here? Well, it's that h of x is an integral. We can say d fourth y, delta fourth of x minus y, h of y. Well, that's just a triviality. But on the other hand, delta fourth is minus box on pi. And so this is equal to an integral d fourth y minus box y pi of x and y, h of y, and now we can integrate this by parts, and we get minus, but it's a quadratic operator, so we don't get any minus sign. And d fourth y, what we then have is pi x and y, box y of h of y. All right, so that's our solution. That corresponds to, I don't really see what it corresponds to at the moment, but anyway, that's one way of writing this thing. This is kind of almost a triviality here because it started out with a triviality. But the next thing we can say, we have an equation here that is box h equals j. So we can put a j here. In other words, we go down here, we can say box y, h0 of y is j of y. And so what we've generated here is h0 of x is minus integral d fourth y pi of x and y j of y. All right, so that's our solution, our lowest order solution. And then the part that looks like this, the way we would generate that is we'd say box w on h1 of w is lambda h0 squared of w. And that is lambda d fourth y pi of w and y j of y times, say, d fourth z pi of w and z j of z. And so altogether then we would say that h of x is this term, h0, which is minus d fourth. If we rewrite the thing, we can, yeah, that's d fourth y. It's just sloppy here. Pi of x and y, j of y, plus lambda integral d fourth w, d fourth y, d fourth z, pi x w, pi w y, pi w z, j y, j z, plus higher terms. All right, so I don't know. I'm not thrilled by this sort of this kind of calculation. However, it does very, very well for quantum electrodynamics, and one can compute things to high order. So I must not cast any aspersions on this. We can write this diagrammatically by saying something like this: h of x equals x or jy plus x w jz jy. All right, and we can think of this as a space-time Feynman diagram if we want. So the idea is you draw a point x, you draw a line to some other point, you put a j there, or you draw a line to some point, you let it split, and then you have two j's. Why do you let it split? Well, because the equation was box h is j plus lambda h squared. So it's the square here that means you split. If it were a cube, you'd split it into 3. All right, I think that's enough for that. the book goes into a little more detail. All right. I want to now answer or say a little bit more about the Noether occurrence and the energy momentum tensor and your question, which I'm going to boost up to Lorentz transformations rather than just rotations, so we might as well do them all at once. And it's basically, again, essentially the same thing as what I did for energy momentum tensor. It'll be a little bit different. This, in a certain sense, is I'm doing one of the homework problems, not one that I assigned, but I don't know, problem 3.2 or something. Anyway, let me first of all review how we got the energy momentum tensor. And remember, that was this: partial L, partial XA equals partial, and I'll do this for one field. Each time, though, you see a field phi, if you want, add a subscript n and sum over n. So you can do this if you do this for many fields. Partial phi, and now this would clearly be the 8th derivative of phi. Let me introduce a notation here that I think is good. Maybe it'll be strange to you, but I'm going to write this. We've been writing this way: dA phi is partial phi partial XA. I'm going to also say that this is phi sub comma A. It just means that instead of writing partial and x, you just write a comma. And if you were doing dB upper of phi, this would be phi upper comma B. It just saves chalk. And the other thing is that it saves neurotransmitters, because your brain doesn't have to record all these strokes here. Okay, so going on with this, the next term is plus partial of L, partial. Now you see the utility of this. You can write this as phi comma B, and then say partial of phi comma B partial XA. Right, so it looks a little bit simpler. And now we can assume, we're assuming, whenever we're talking about the energy momentum tensor and such things, we are assuming that the field equations are obeyed. So since the field equations are obeyed, we can rewrite this as dA partial A partial B actually. Phi comma B, phi comma A, and there's where the derivatives act, plus partial L, partial phi comma B, partial phi comma A, dB of that, so there, dB partial of phi sub comma A. All right, and then all of this can be written as dB of partial L, partial phi comma B, phi comma A. And on the other hand, this can be written as dB of delta BA L. And so altogether we get 0 is dB of, the first one is partial L, partial phi comma B, phi comma A minus delta BA L. Okay. And this thing is then dB T BA. So this is the we call this dB, JB, and JB is the current, a conserved current, TBA. A takes on 4 values, so there are 4 conserved currents. These are the energy momentum currents. Okay. So that's how we did things for changes of, for the translations. And what we're going to do now is rotations, and here's the way I'm thinking of them. I'm thinking here we have x prime A is, remember, what we had is something like this. So theta is a parameter, omega is a matrix, the generator. All right? And this gives you a matrix AB, XB. And so now what we're going to be looking at is partial x prime A, partial theta. Well, this is just omega AB on this thing, either the theta omega BC XC, but this is just x prime, so this is omega AB x prime B. So basically that's how x has changed. It's not in the book.
No, just flipping.
All right, okay. So this is how it's changing, and now we're just going to drop the prime and say partial x partial theta is omega AB on XB. Now, remember, however, that these guys, this matrix omega, there are 6 of them, 3 for rotations, 3 for boosts, and they have no diagonal elements. They're entirely off diagonal. And the rotation generators are anti-symmetric, and the other ones, the boost ones, are symmetric. Well, anyway, they're back. There's something I covered, and they're also. I think did I post chapter 10 on the chapter on tenses? I put it on my book, chapter on tenses. I put it on the web page. It's in there somewhere. Oh, no, it's chapter on loop theory. Well, maybe I'll have to post that as well. Okay, so let's keep in mind a particular generator. It might be for a rotation about the z-axis. It might be for a boost in the y direction, whatever. So let's compute partial L, partial theta. Well, this is going to be partial L, partial phi, partial theta, plus partial L, partial, the 8th derivative of phi, and then dA, partial phi, partial theta. Once again, we're going to invoke a field equation. So this is dA, partial A, partial phi comma A, partial phi, partial theta, plus partial L, partial phi comma A, dA, partial phi, partial theta. And now we see this thing is a total derivative. It's dA. So this is very much like what we had before. Partial L, partial phi comma A. Of course, you notice that my left arm is down, so you need to watch me like a hawk. Partial phi, partial theta. So the first, if it acts on this, you get the first term. If it acts on that, you get the second term. Okay. This is if we're assuming the field equations are obeyed. And now we're also going to say that what is partial phi, partial theta? Well, partial phi, partial theta, this is phi comma b, in other words, the derivative with respect to xb times partial xb, partial theta. And this is phi comma b, omega bc, xc. So that's this equation here without the prime. Okay. But now we need to do some shenanigans with this part, the way we did over there. And it's, I found it a little bit trickier. It's partial L, partial theta. Well, we can call this the Beeth derivative of L, and then we have partial xb, partial theta, like that. Okay. And so that's dBl times omega bc xc. Okay, now here's the cute thing. First of all, we're talking global symmetry here. In other words, we're doing a rotation that's the same everywhere. If we wanted invariance on the local rotational symmetry, if we wanted to gauge the rotations and gauge the groups, then we'd be in full-blown general relativity, or others a gauge theory. So instead, we're talking about omegas that don't depend on x. Not only don't the omegas depend on x, but omega has no diagonal elements. So this Beeth derivative here, if we said instead of having it dBl, if we let it act to the right here, we wouldn't be getting anything wrong, because the Beeth derivative can't give 0 when it acts on xc, because c can't equal b, because omega cc is 0. So I'm going to do just that, dB L omega bc xc. All right, so now we have our field equations. Namely, we can say 0 equals dA of, and it's partial L, partial phi comma A, phi comma B, and that gets multiplied by this partial phi partial theta, and partial, let's see, I didn't bother to do that already. All right, so let me do this a little bit more slowly. This is partial phi partial theta, and then it would be minus delta AB, and I've already done this part, so let me call this L omega BC XC. And this thing here, partial, oh, I've already done that, it's up here. Okay, so let me stick that in down there. So using this for the partial phi partial theta is partial xb partial theta is omega bc xc. So this is omega bc xc. So altogether this is much simpler. It's partial A of partial L partial phi comma A phi comma B minus delta AB L, all that times omega BC XC. All right, and I should put this over there like that. And what I'm doing then is I then wrote this as dA delta AB L omega BC XC. Just trivial rewriting of this. Are we all happy? All right. So this is our expression. Now, this, see, is what we had earlier. This is just TBA. This is the energy momentum tensor. So the answer is then we have 0 is dA of T, and in this case it's AB, dAB times omega BC XC. So these are the conserved currents due to rotational and Lorentz invariance. or Lorentz invariance includes rotations actually. So the current then is JA, which is TAB omega BC XC. So that's our conserved current. And now, how many of them are there? There are 6 of them, because there are 6 different omegas. 3 for rotations, 3 for boosts. Okay. All right. So now let me explain this in a little more detail for the case of rotations and boosts. All right. So let's just see. All right, if we have, so as an example, if this thing is a half partial AV, partial AV minus a half m squared v squared, which is just a scalar field of mass m, then of course partial L, partial phi comma A is just phi comma A, and so JA is phi comma A, phi comma B minus delta AB L, where that's L, and then it's omega BC XC. So those are the 6 currents. Now, let's look at a scalar field, and let's look at the thing that's conserved. Well, the thing that's conserved is the space integral of J0. And again, as I said before, when you have a conserved current, the thing that's time independent is the spatial integral of J0 and whatever the surface terms happen to be. So in other words, what the conserved current tells you is the time integral of J0 in a certain region is minus the stuff leaking out. And so you always have to keep track of, you always have to think in terms of the stuff leaking out, especially for the case of energy, momentum, rotations, boosts, and so forth. All right, so now, what are these rotations? Well, the thing we want to look at then is an integral of J0 d cubed x. And in the case of rotations, this is a 0. Rotations only involve spatial indices. So if you forget this. So all we've got then is an integral of A is 0, so that's just phi dot. And dB, well, B has to be spatial. And because the B's are only spatial for rotations. So effectively we can say this is grad phi, and then we can essentially put a 0, a vector on this and do all 3 at once. And then what do we have? We have omega BC, omega's antisymmetric, and an x here. And so this is effectively the cross product of the gradient with the space vector x d cubed x. So it's that cross product effectively. That's the thing that's the angular momentum. conserved, modulo a certain term. Okay. All right. Now, what is this thing here, though? This thing is, in fact, the density of momentum. In fact, it's then the stuff whose, in other words, if we were integrating J0 for the momentum, we would have here simply phi dot grad phi d cubed x. So this, we can think of this as momentum density cross position d cubed x. All right, so shoot me, I've got a minus sign here. Obviously, it should be r cross p rather than p cross r. So I'll just sneak in a minus sign here. But of course, the minus sign is because, you know, this omega, we can have plus omega, minus omega, and so forth. Okay, so that's the what's conserved for rotations. Now, here, let me just say something here. Snuck in my minus sign. What if we had vector fields instead of scalar fields? Well then, the derivatives here with respect to, in other words, what's happening here is we would have AA of theta. So I'm emphasizing the theta rather than the x. And so this would be either the theta omega matrix AB, and the x here is either the theta omega x, thought of as a matrix. Okay, so this is how the, say, the electromagnetic field transforms. So now what is partial A, partial theta? Well, there's one term that's just omega AB on AB, and then there's the term that we had before, dB AA, omega BC XC. So this is what we had before with phi replaced by AA. And this is the new thing. All right. So now, what is the conserved current? Well, it's a little more complicated. GA now is partial L, partial AB comma A times omega BC AC plus AB comma C omega CD XD minus delta AB L omega BC XC. All right, that's what we have. This part is what we had for scalar fields. So this gives you angular momentum and whatever you get for boost. And I'll get to that in a moment. This, though, gives us something new. And this is the contribution to the angular momentum of the spin of the photon, or it's a field of spin 1, and this is how the spin contributes to the angular momentum, and also how it contributes to whatever it is that's conserved for the case of boosts. All right, let's turn now to boosts, and let's go back to the scalar case. And okay, like this. Well, there have been almost no questions. Also no jokes. I'm short of jokes again. I don't know what it is.
obvious that the new piece is a spin type?
Hold on a second.
No, thank you.
You don't want it.
No.
All right. What was the question?
So should it be obvious that the new piece that we discovered with the vector
Yeah.
is a spin type? That it acts like spin?
What else could be? Mosquitoes?
I mean, you could call it whatever you want, but by calling it spin, you seem to be very deliberately trying to lead us to that.
Load the dice?
A little bit. A little bit.
You're a hard man. I don't know. I mean, you know, I mean, it's gotta be the spin. What more can I say?
I guess that's all that can be said.
I mean, you could use that as a definition of spin if you want. All right. Let me now get to what's conserved because of boosts. And here, the answer is almost comical, but it's not funny enough to make up a lag of jokes. All right, so let's look at the thing that's conserved. J0 d cubed x, and now we're thinking about boosts, and so we have this thing. And remember, when we have a 0 here, and so remember the other way of writing this is to say that JA is TAB omega BC XC. And so in this case, it's T0 B omega BC XC d cubed x. Okay. And now, a B can be either temporal or spatial. If it's spatial, then we have T0I, omega I0, and now C is 0, so that's T, d cubed x, plus integral T0, 0, and now B is 0, so this is omega 0, and now this has to be an I, and so this is xi t cubed x. Okay. Well, this is the momentum density, and it's dotted into these, and so we can say this is the momentum in a particular direction. What's this? This is energy, and this is position, and so this is something like, I'll put a minus sign here because I want to. Something like energy density times position. And if we go to the very simplest case of just imagining that all the fields are concentrated at one point, then what we've got is that the conserved quantity is P minus E x. So, and let me go back to vectors. So those are the three things that are conserved. Momentum minus energy times position. Why is this conserved? Well, it's that, oh, I'm sorry, I left out a T. T. Okay, but we're also considering the case where E and P are already conserved because energy and momentum are conserved. So now to differentiate with that with respect to time, we get P is equal to EV. Okay. But in fact, that's the relativistic form for energy and momentum because P is mv over the square root of 1 minus p squared. Again, I'm just going to a single particle just to illustrate it with a very simplest case. Okay, so it's sort of a comic letdown that we have here this invariance under boosts, and you think, oh, this is really mysterious, the thing that's conserved must be something special, and it turns out to something that, you know, it's, I mean, PT minus EX is something that, you know, it's freshman mechanics, at least in the relativistic part of the course. All right, so any questions before I go on to next talk? All right. Okay, well, I think then that we finished chapter 3, so I'm going to start chapter 4. I'm going to try to get through 4 as quickly as possible because I don't think we want to. I don't think we want to make it terribly deep. The homework problem is 3.5, so that would be due, I'm saying it should be due, today's Monday, right? You have Wednesday, not this Wednesday, but next Wednesday. It's just one problem. It's not a hard problem. All right, so let me go over there then and try to. This business, the topic here is yes. The topic is the Lippmann-Schwinger equation, and this is something that's rather cute in many ways. It has to do with, it's used a lot in the case of, well, it's used a lot in the case of non-relativistic potential scattering in quantum mechanics, and it's sort of cute, so let's just do it. So, the idea here is we have the soluble Hamiltonian, H0 phi is E phi. And now, when we're talking about scattering, we're talking about positive energies. So, we can imagine that we also have states that are eigenstates of the full Hamiltonian with the same eigenvalue E, okay, because we're talking about a continuum of positive energy states. All right, and then we say, well, H is H0 plus something that makes the energy impossible to diagonalize, or very hard, let's say. And so the thing we want to solve then is H0 plus V on psi is E psi. All right. And we can rewrite that as V psi is E minus H0 psi. Okay. But on the other hand, we can generalize that, and we must. Because if we stick in any multiple of the eigenstate of H0 with eigenvalue E, this is still a true equation because E minus H0 annihilates P. All right, so there we are. We just rewrite this now by dividing by E minus H0. And then what we have is psi is equal to phi plus 1 over E minus H0 V acting on psi. So that's the Lippmann-Schwinger equation, that the eigenstate of the full Hamiltonian is the eigenstate of the free Hamiltonian with the same energy, and to the extent, and lowest order perturbation theory, that's all we have. And then we add in this expression here. And the cute thing, you see, is that it's such a simple formula. On the other hand, we've got the unknown on the right-hand side, so we're not done when we write this down by any means. And the next step, which I imagine Lippmann-Schwinger took, Schwinger was very sharp, I must say. So V on psi is defined to be T on phi. Okay, so this is, so in other words, we've got V on psi, and we don't want that because we need a phi over there. So we say, well, T is whatever we need to do to fix the fact that we have a psi here rather than a phi. And once we do that, then we've got phi plus 1 over e minus h0 v psi, well, that's T phi. And now we've got a very nice expression, because we can say the thing we want is 1 plus one over e minus h0 v on the thing we know. Okay. And let's see, there's another way of writing this. I don't know if that's all that. Yeah, I better do that. Okay, so we have this expression here, and let's see.
Should be D there instead of V.
I've got this written down in front of me, so let me write it down, and then maybe we'll see why it's true. Right? Oh, V.
Should be D.
This is what I have written in my notes, but I'm a little bit, yes, that's right, okay. So we just saw that psi is this, so V psi is V times psi. Well, psi is 1 plus 1 over e minus h0 times, oh, this is a V.
No, it's a T. It's supposed to be a T. No.
Oh, there's a typo in the book?
No, it's a T in the book.
It's a T.
Anyway, V.
I think it's supposed to be
You're gonna
a
make
T.
it worse.
I'm making it worse?
Yes.
Yeah, it should be.
Because the
It's supposed to be-
equation down says that it's a T.
The second equation, you have 1 plus 1 over e minus h naught v. That v is supposed to be a T.
This is supposed to be a T?
Mm-hmm.
Yeah, that comes from the down equation.
All right.
And then change that.
Oh, that
one
comes
back
from
to
here.
T.
Yes.
Okay, good.
And then you gotta change the second v. to
All right,
T.
okay. And so then we say V psi is T phi, and now V psi, this is T, isn't it? And so that's that, right?
Yeah.
That follows from that. And on the other hand, V psi is this. Okay, once we have this equation, we then promote it to, we say, well, the phi's form a complete set of states, and so we can promote this to an operator equation. And then what we have is T is V times 1 plus 1 over e minus h0 T. And so that's the operator version of this. And now, if I have a little more space, let me go over here, I guess. Okay, so now what we can say is that moving everything to one side, we have 1 minus v, 1 over e minus h0 t equals v, and so then t is 1 over 1 minus v, 1 over e minus h0 v. So this is our equation, and this is actually a solution because everything on the right-hand side is known. And of course, we can then expand that if we assume that this is small. Now, is it really small? Well, there are eigenstates of H0 with eigenvalue E, so that's 1 over 0, so this isn't necessarily small. But in the spirit of perturbation theory, which I've never liked very much, we imagine that V is so small we can ignore that problem. And then what we get here is a sum, n equals 0 to infinity, of V 1 over E minus H0 to the n V. So our T matrix then is an infinite series times V. And this infinite series is, for n equals 0, T is V. For n equals 1, it's V 1 over E minus H0 V. And then the next one is V 1 over E minus H0 V, 1 over E minus H0 V, and so forth. Plus. Okay, so that's basically all I have to say for now. Maybe there are questions? Yes?
So V and H naught, all these are operators.
Say it again?
V and H naught, all these are operators.
Yes.
So we have this T.
T is an operator also.
But you have, oh, okay, I see, yeah. Right.
All right, so so that's that, and see you all Wednesday.